All right, today I'm going to spend a few minutes wrapping up our DNF counting story, and then we are going to get into classical graph algorithms like minimum spanning tree and minimum cut and things like that. So last time we talked about DNF counting. And the sort of core problem with DNF counting was this rare event problem. Where we had a formula, right? But the probability that it was true could be tiny. And so we couldn't use the standard sample and estimate approach. It would take us too long to get to that magic mu epsilon delta number of true formulas. So what we did was we changed the sample space. So that the probability of truth is large, right? And also, we know the size of the sample space. Right? And all we needed was these two things, right? If we know the number of points in the sample space, assuming uniform sampling, right? If we know the number of points in the sample space and we also know that the probability of truth is large, then we can count the number of true items by using standard sampling to estimate the fraction of true items and then multiplying by the number. Yes? So really, this is all that we needed, was a sample space where the true occurrences are large enough. Okay? But if you step back, the way we did this was we had a algorithm for generating samples, and we used it to make an algorithm for counting the number of satisfying assignments. Yes? All right. I want to tie these together more closely by going into the other direction. Okay. Now, I mentioned last time that our counting algorithm could actually be seen as an algorithm for generating satisfying assignments uniformly chosen, right? Because, you know, in our model with its circles and x's, right? The circles are a single copy of what we want, right? One of each satisfying assignment. So by generating a random circle, we are choosing uniformly among the, by sampling a random circle, we are actually getting a uniformly distributed satisfying assignment. And our procedure of just sampling x's until we see a circle runs fast enough to do that, right? Because the sample space is not too large, or to put it another way, because the circles are reasonably common in the sample space, right? This is a particular example of what's called rejection sampling, where if you want to sample from a hard distribution, you find an easy distribution that it's easy to sample from, and then you use a procedure to reject things that are not in accordance with the distribution that you actually want. And in your homework this week, I will give you a sort of a more general question about rejection sampling so that you can explore how that works. Okay? But now let me come back to, so we had a direct generation algorithm, right? But let me go back to, let's assume that our counting algorithm, we didn't know anything about it. It's a black box. All it does is tell us the number of satisfying assignments. I claim that this is enough to let us generate satisfying assignments uniformly at random, no matter how the counting algorithm works. And all we rely on is this good old-fashioned idea of self-reducibility. So we've already talked about self-reducibility once in the context of matching algorithms, right? You find one edge that is in a perfect matching, and then you end up with a smaller perfect matching problem that you can solve recursively. And I mean, self-reducibility is very intimately tied in with recursion, right? That basically, if you have a recursive algorithm where you sort of pick part of the solution and then recurse, that leads you towards self-reducibility. And if you think about it, DNF has this nature, right? If I set the value of a particular variable to be true or false, I can partially evaluate the DNF, right? And I can be left with a new DNF formula, right? And that DNF formula has certain satisfying assignments, right? So if I set the first variable to true, what do those satisfying assignments of the new DNF formula correspond to in the original problem? Yes? Great. So that's the procedure for generating the new formula. And what does that new formula give us? If we talk about the solution, the satisfying assignments for the new formula, what are they? Right? So we start with a DNF that I'll call A, right? We will partially evaluate it with x1 set to true. And that gives us some new DNF B, okay, according to the algorithm that you described. Now, if I talk to you about the satisfying assignments for B, what are they? Yes? Exactly, right? So satisfying assignments for B are satisfying assignments for A with x1 true, right? I can do the same setting x1 false. And then I get the satisfying assignments of the original formula that have f1 set to false, right? And this points at a natural recursive algorithm for finding a satisfying solution, right? You try setting x1 to true, and then you recurse, right? And if that doesn't work, then you set x1 to false, and you recurse, right? So this gives us an algorithm for finding a satisfying assignment. Unfortunately, it's exponential time, but it is an algorithm, right? It's a natural recursive algorithm. The point is, this actually is kind of, if you remember our game tree evaluation, right? This is evaluating a big binary tree looking for a win, a satisfying assignment, right? Suppose that instead we want to do generation. Via counting. Okay. Suppose that I do the following. Actually, let's call this B prime. Okay? So I've got a formula that I generate by setting x1 equal to true and partially evaluating. I've got another formula that I can generate by setting x1 to false and partially evaluating. Okay? So now, let's set C equal, remember, I have a counting algorithm, right? So I can count the number of satisfying assignments in clause B, or in formula B, and I can count the number of satisfying assignments in formula B prime. I claim that with this information, I can take a step towards generating a random satisfying assignment of A. What should that step be? Suppose, for example, that C prime was 0. There are no satisfying assignments where x1 is false. Okay? What can I do to move towards to generating a satisfying assignment? Yes? Exactly, right? What we can do now is, you answered the general question, but I'll go there, right? What we do is randomly set x1 equal true or false with probability c over c plus c prime or c prime over c plus c prime, respectively. Right? So essentially, right, these two numbers, c and c prime, these tell me the probability that x1 equals true conditioned on having a satisfying assignment. Right? And once I know that probability, I will just set x1 to be true with that probability. Right? And now I can recurse. I can generate the rest of the formula using exactly this procedure. Right? And hopefully it is, like, tell me if you'd like to see it worked out in more detail, but hopefully it is clear that if I just repeat this procedure one variable at a time, I will get the correct distribution. Right? One intuitive way to think about that is to say, again, game tree evaluation, right? So essentially, we can imagine that we are evaluating a tree of possible settings of variables where we set x1 at the first level and x2 at the second level, and so on and so forth. The point is that we know how many paths work in each direction. So if I choose my path start with probability proportional to the relative numbers here, I will be on the first step of choosing a random path. Yes? So kind of like in the game tree evaluation, right, the non-deterministic algorithm sort of evaluated everything. Here, we're picking a random direction to go down, so we're not exponential, right? We're just walking linearly down the tree. So this shows how with self-reducibility, you can basically turn any counting algorithm into a generation algorithm. Any questions about that? There's one that is kind of begging, given what I presented so far. Do we have a counting algorithm? Yes?
Yeah, last lecture we made a counting algorithm.
Well, was it an actual counting algorithm? Exactly. So it's no harder, but takes a little bit messier notation to show that you can transform an approximate counting algorithm into an approximately uniform generator. Okay. And by approximate here, I mean FPRAS. And FPRAS is important because if we want to be within epsilon of accurate, well, we have n steps where we're going to be using our approximate counter, and the errors are going to accumulate. So we're going to need to set a target epsilon within our counter, which is like 1 over n of the epsilon we want to end up with, right? But fortunately, the FPRAS has a runtime that's polynomial in the error. So dividing the error by a factor of n doesn't really, you're still polynomial. Okay? All right. And just to close the loop farther, I will also mention that if you have an approximate generator plus self-reducibility, you can get an approximate counter. Okay. So here, again, without knowing anything about the black box, suppose that I just have a tool that will generate satisfying assignments. Okay. How can I go from that to counting satisfying assignments? Well, we're going to again want to focus on x1. Okay, so this time what we say is by generating we can use the sampler to tell us the probability that, sorry, let me see how I want to say this. Let's do it this way. Generate many samples. Some have x1 equal true. Some have x1 equal false. Right? The thing that you can work out is that you can use these relative counts to give you an estimate of the probability that x1 is true in a sample, or an estimate of the probability that x1 is false. And that gives you a first step towards counting. Okay? And this is something you work out in detail in your homework. But with that put away, I want to focus now on minimum spanning tree. Okay, so until now we've been sampling to count things. And so we've been focusing on numbers. Now we're going to start sampling structures in order to actually solve algorithmic problems. Okay. I'm going to start by talking about minimum spanning tree. And the intuition is going to be the same, that a sample is representative of something. And you use the sample to give you insight into the space of solutions. But now we're going to be getting structural insights instead of counting insights. Okay. So what do we know about MST? This is a problem that we studied in advanced algorithms. So a quick rundown, right? We've got Prim's algorithm, and we've got Kruskal's algorithm, which are the two that you always learn in your introductory algorithms classes, right? And with Fibonacci, and they both have a running time of order m log n if you implement them in the naive ways, using sorting and or using standard binary heaps, right? Now there's a third algorithm that some have seen and some have not. It's actually the oldest of the bunch. Does anybody know which one I left out? Just sort of fundamentally different? Yes?
Maybe
Boruvka's algorithm, right. So, right? This is actually from 1926, right? I don't know what he was doing inventing algorithms before there were computers, but there you go. I don't need to say a lot about Prim's and Kruskal's algorithm, but and I assume that you remember them, right? I will mention that Kruskal's is based on sorting and then adding edges one at a time if they are not connected by a path of smaller edges, right? And this, the correctness of this is based on a feature of minimum spanning tree. I forget whether it's the red rule or the blue rule. It's got one of those names, right? Which says that an edge is in the MST if and only if it satisfies this condition. Right? And so going through the edges in sorted order is just an efficient way for you to detect that and say, aha, all of the smaller edges do not connect the endpoints of this edge, therefore this edge is in the minimum spanning tree. Okay? And we're going to use that principle. Okay. Boruvka's algorithm, very different, but it actually uses the same, it relies on this principle as well. What you do is take the smallest edge, incident, on each vertex. Okay. And I claim that all of these are in the minimum spanning tree. Can anybody see why that's true, given the rule that I just stated? Well, I should say right at the beginning, I'm going to assume there are no ties. All the edges have different weights, so that we don't have to talk about tie breaking. Yes? Exactly, right? So suppose the smallest edge is not in the minimum spanning tree. It means there is a path of smaller edges. But if you think about it, one of those edges has to be incident on this vertex, right? So it's not a path of smaller edges. Okay. So all of these edges are in the minimum spanning tree. I can contract all of these edges. We've already talked about contraction in the context of the contraction algorithm. What can we say after the contractions? Well, in the contractions, each connected component turns into a vertex, right? But what can I say about the connected components? Well, each one has at least two vertices, right? Because every vertex has a smallest incident edge, and so it's connected to something else. So there are no isolated vertices. Every component has at least two, which means that you have at most n over 2 components, which means that the time to solve an m-edge graph with n vertices is the order m time that it takes to find the smallest vertex, the smallest edge incident on each vertex, plus now you've got an m-edge graph with only n over 2 vertices, and so this gives you yet another m log n time algorithm. Okay? And yeah, this was probably a whole lecture in introductory algorithms, right? Was Boruvka's algorithm, but you can see that it's pretty straightforward. Yes? All right. So those are the algorithms. Oh, I should also mention, since we talked about this in advanced algorithms, that if we use Fibonacci heaps, which are a data structure that we cover that allows insertion in constant time instead of log n time, but still takes log n time for delete min, you can improve the runtime of Prim's algorithm to m plus n log n instead of m log n. And then if you go really crazy with various kinds of recursion, you can get this time down to m log star n or so. So very close to linear, but not quite. Okay, this is like the I such that taking the log of m I times is less than 2 or something like that. Okay. All right. So this progress was made in the 1980s. People figured out, wow, we're really close to linear. Surely it's just a few more years before we get linear. Yes?
Do linear time with Puskás using
if your numbers are represented in a small number of bits, so if sorting is linear, it's still not linear time because you need a union find data structure. Okay, so there are these two things pushing you away from linear. So people worked on verification, couldn't really progress beyond this log star n. Komlosh, so because constructing was hard, people looked at an easier problem, which was verification of a minimum spanning tree. We've talked already about verifying versus constructing. How hard is it to actually, if somebody gives you the tree, how hard is it to tell you that it is in fact the minimum spanning tree? Right? And so the first progress here was by somebody named Komlosh, who proved that you can do the verification with order m comparisons. Unfortunately, it takes like n to the fourth time to figure out which ones. All right. So if you're only counting comparisons, you're good, but it doesn't work as an algorithm. There is on the plus side, it doesn't only tell you whether it is the minimum spanning tree. It tells you which edges are F light. And here, F is the candidate minimum spanning, and I'm going to say minimum spanning forest. It doesn't actually have to be a fully connected tree. It might just be a bunch of pieces of tree. All right? But this algorithm will tell you all the edges that are not connected by the lighter edges in F. Okay, so this again relates to the red rule, or maybe it's the blue rule, right? If you are connected by the lighter edges in F, that means that F has proven that you do not belong in the true minimum spanning tree, right? So this finds all of the edges that violate the idea that F is the minimum spanning tree. Okay. I will also mention that the MST edges themselves are F light for any F. Because that's the definition, that's, again, the if and only condition for minimum spanning tree, right? Even if you take the whole graph, the minimum spanning tree edges are not connected by a set of lighter edges. And so certainly for any forest, they're not connected by the lighter edges. All right, so that was promising. Komlosh gave order M comparisons. And finally, I think in the 90s, or maybe the late 80s, Dixon, Rausch, and our old buddy Tarjan, who I think you all remember from advanced algorithms, gave an order M verification algorithm, which also does the output of all the F light edges. And the way they did it was basically brute forcing. So what they did was they said that they built a lookup table for all tiny trees using the Komlosh algorithm. So basically, for some target size k, you enumerate all of the trees of size k, and then you run Komlosh's algorithm on each of them to find out what comparisons should be used for that tree. Okay? And if k is small enough, you can do the enumeration of all the size k trees and the construction of their verifiers in order n time. Okay. Then they basically use all of these crazy algorithms to sort of reduce the problem of verifying a minimum spanning tree to verifying tiny spanning trees, right? And they verify those by looking in the table. All right? So it's essentially a brute force exponential enumeration. They're just clever about what size they do it at, and this gives them the verifier. Okay? So that's where things stood in the 90s, that we had a linear time algorithm for verification, and we were really close on construction, but we didn't know how to get that last bit. So, turns out a trick that works is random sampling. Okay. We're now working on sampling structures. If you have a graph, what might be a plausible thing to sample in order to give yourself insight about what the minimum spanning tree looks like? And what might the intuition be about what it would tell you? Right? You've got this big, complicated graph. You want to learn something about it. How might you get something smaller that tells you something useful? Well, there's not a lot here, but I would argue that the most obvious thing to do is to take a random subset of the edges. Okay, and I'm going to denote this by G of P, which is stealing notation from the theory of random graphs. So I talked a little bit about the theory of random graphs, where you basically have a set of vertices and you put in each edge with probability P, right? And this led to this incredibly rich literature on the structure of random graphs and when are they connected and what is their coloring number and what's their diameter and so on and so forth. All sorts of interesting problems. This is just generalizing that notion to talking about, so that random graph is basically saying all of the edges are candidates. I'll pick a random subset of those. This is just generalizing to say I have a starting graph and I choose edges only from that starting graph. So it's a random subgraph of the starting graph. Okay? So, what might intuition suggest about what this could tell us about the minimum spanning tree? Right? Another thing I'll pull back into your memories is when we were doing median finding. Right? We said if we take a subset of the elements in the list, it gives us sort of a ballpark about where the median is, right? We set up these fences, things that are slightly above and below the median, and it didn't tell us exactly what the median was or anything about its value, but it told us the median is between these two values, these two elements, right? So what might our intuition be regarding a subset of the edges? Yes? Sorry, say again? Good. So that would be a nice intuition to start from, right? Is that when we take a sample, we get most of the edges of the minimum spanning tree, right? But this intuition breaks down pretty quickly because we're choosing each edge with probability P, right? So if P is small, we're probably not picking most of the edges from the minimum spanning tree. right? So is there any hope that it might be helpful? Yes. Ah, good. So maybe you should use non-uniform sampling and choose small edges with high probability and large edges with low probability. So this collides with the fact that the MST is not determined by the weights of the edges, but only with the relative order, right? So if I square all of the edge weights, it doesn't change the MST. Or if I exponentiate all of the edge weights, it doesn't change the MST. So whatever my sampling strategy would be, it would have to depend on the order of the edges in order to be robust. It couldn't depend on the values. And if it depends on the order of the edges, then the only way I can construct the sample is probably involves sorting, which is too slow. Okay, but that's a good, it's a good thought to try that. Okay, again, look at our rule here, right? An edge is not in the minimum spanning tree if it is. An edge is in the minimum spanning tree if it is not connected by a path of smaller edges. So what might we hope for our sample? I mean, our sample is going to have a bunch of edges in it, right? So what might that sample let us do? Yes? Exactly, right? The sample is going to have a bunch of edges, and essentially those edges can demonstrate that some edges do not belong in the MST because the sample has a path that rejects the edge, right? And in a sense, if the edge is very not in the minimum spanning tree, if it has tons and tons of light paths connecting its endpoints, then we would hope that our sample picks one of those paths and knocks out that edge from consideration, right? So that suggests that what we now do is, construct some forest F as the minimum spanning forest of G of P. And I write minimum spanning forest here because the sample that we pick might not connect G, right? We might completely miss out on some connections. It's okay. We can still talk about the minimum spanning forest of a disconnected graph. It connects everything that it can connect, right? And doesn't worry about things that can't be connected. Now we can run a verifier and find all the F-light edges. And then we can construct, let's call this L for light. And then we'll construct the minimum spanning tree of the light edges. Okay. And I claim that this algorithm is correct. Why is this algorithm correct? Regardless of what sample we choose. Yes? Exactly, right? The true MST, correct, true MST is inside of L. Therefore, the minimum spanning forest of L is equal to the true MST, right? Taking away edges through this verifying process does not make this minimum spanning tree worse, right? We're not going to take away any actual minimum spanning tree edge, and so the minimum spanning tree is still there to be found, and nothing got better from our subtraction of edges. Correct? Okay, so what is the critical question? Yes? Exactly. The performance of this algorithm is entirely determined by how many edges are F-light when you take your sample. Okay. All right, so This is a project that I was working on in graduate school, and I got this far, and I came up with an incredibly contorted algorithm that gave analysis that gave a bound on this, which was off by a factor of log n, and therefore yielded all sorts of other weird algorithms for minimum spanning tree with running times of m log n, because it was off by a factor of log n. But then, two people, Phil Klein, colleague at Brown, came up with an absolutely beautiful analysis of this question, which cracked open this problem. Yes?
What does it mean, like, run the verifier to find the f-like edges? Like, once if we correctly construct the maximum spanning forest, doesn't that already imply the f-like edges?
Well, if you correctly construct the minimum spanning forest of the original graph, then all of the edges that are not MST edges will be f-light for that forest. But here we construct the minimum spanning forest of a sample. So, for example, any minimum spanning tree edges that we did not sample are going to be light for this forest. So you are going to get a larger set of light edges. You are not going to have, in general, a tree of light edges. So you get some set of edges, and you know that the minimum spanning tree is in there somewhere, but it's still a minimum spanning tree problem. It's just on fewer edges, hopefully. Okay? And so if you think about it, essentially what we're doing here is we're turning into one big minimum spanning tree problem, one MST problem on a large graph into two MST problems on hopefully small graphs with fewer edges. Right? One in our sample and one in whatever the f-light edges are. Okay. So here's the critical theorem. Okay. Which is that if you construct f equal to the minimum spanning forest of G of P, then N over P, N over P edges are f-light. So before proving this theorem to you, let's try plugging it in. Okay? So how long does it take me to construct the minimum spanning forest of G of P using my favorite known MST algorithm? Well, what determines the running time of my favorite? Sorry, I won't say favorite. Let's use a naive algorithm so that we don't have to get into contorted runtimes. Okay, Prims, Kruskal's, Boruvka's. How long does it take me to construct the minimum spanning forest? Yes? Exactly, right? PM log n, right? Because the sample has about PM edges with high probability. Verification step, that's order M, thanks to Dixon, right? Then how long does it take me to construct the minimum spanning forest of the light edges? Yes. Exactly. So we put these together, and we get a runtime of order mp plus n over p log n. So what should I do? Yes?
You want to set like MP and then over P like equal?
Exactly,
So
right?
it's going to be something like so like P is going to be something like root of m over m.
Exactly, right? So I have one, if I think about increasing p, this term increases and this term decreases, right? One's going up, one's going down as I vary p, right? From an asymptotic perspective, the point where they meet is asymptotically optimal, right? Because at any other place, one of the two values is going to be larger than this. So this is within a factor of 2 of the optimum possible solution, right? Because at this point, both of them are matching, and each of them is less than whatever the larger of the other two is, right? So basically, I'm saying the sum is less than twice the, or sorry, I don't want to get myself tangled up here. The sum of two values is less than twice the maximum of the two values, right? And so you set these equal, set mp equals n over p, which means you set p equal root n over m, and that gives you a running time of root mn times log n. Now you have to be a little bit careful about some lower order terms that might dominate. Okay? You do have to scan the edges and vertices for various reasons. All right? So instead of the m log n of Kruskal and Boruvka and Prim, now you have square root of mn, which is better, right? Everybody agree? Yes? It is. But this does not use any fancy data structures, except for the little detail that it's using the verification algorithm. But you have the point is you have a black box verifier here, and however it runs, the outside loop is trivial, right? So I grant you, it is not a performance improvement yet, but let's think about this. I had this procedure that took a MST algorithm and produced a faster MST algorithm, right? This took an m log n algorithm and turned it into a root mn log n algorithm. Now I have a faster algorithm. What should I do with it? Yes? Yeah, I could use this algorithm instead of Prim's algorithm over here, right? So I could sort of iterate this procedure. Right? Now my first step will have a runtime of root pmn log n. Yes?
Why are we iterating instead of just writing down the entire recursion?
Which entire recursion?
Like instead of all of pm log n, just write down like p of m comma n, and then we want to solve this.
Well, because when I write down my t of mn, I'm going to have a p in here. I don't know what p should be. Right now, I could say that t of mn equals min over p of blah, 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 but then I have a minimization problem to solve. Okay? What I'm actually showing you here is kind of how we converged on the proper solution. this is not what you would actually do in practice, but it's a little piece of sort of how researchers figure things out. Okay? So if you try plugging this in again, right, you have root pm n log n for the first time, for the first thing, and also you still are spending only n over p log n in the second step. Yes? So now you want to balance these, right, which gives you a different p to balance these two terms. It's much messier now because there's a root p over here, and I'm not even going to do it. But the point is that you get into this sort of funny situation where each time you figure out a faster algorithm, you can take it and plug it back in to get an even faster algorithm. So the algorithm keeps getting faster each time you apply this observation about sampling and verifying. Okay? And it's kind of like a spiral that sort of spins close, gets tighter and tighter until it explodes at the end. Once you look carefully at it, it turns out that what you should do is just set p. Basically, as you improve this term, the penalty for a larger p gets less and less because you're taking square roots and things like that. So it guides you towards taking larger and larger p. And in fact, what you should do at the end, it turns out, is set p equal to a half. This is where it converges to. And if you set p equal to a half, then you do in fact get a recursive algorithm. T of mn is, well, with p equal a half, you're sampling half of the edges, right? And then you're doing your verification step. And then you are finding the MST of the light edges. How many light edges are there going to be if you set p equal to a half? Yeah? 2n. So it appears that we've kind of run out of steam here. I'll just put in order n log n here because we can use our favorite naive algorithm. Okay. And so essentially, it costs you n log n work to cut the number of edges in half, which gives you a running time of m plus n log squared n, which is at least kind of nice, right? It is now linear unless the graph is very sparse. Okay? So we've made some progress. We're not done yet, but it's 3:30, so let's take a break, and then I will finish this up by proving the sampling theorem and getting rid of this pesky term. Hi. Yes. and I will add this clarification in case anybody else didn't get it. In this step, what I'm doing is I'm taking the minimum spanning forest that I constructed from my sample, but then I'm running all of the edges of G against that minimum spanning forest to see which of them are light. Right? That is why I am assuming an order M runtime for the verification. I'm not just looking at the sampled edges. I know they're all F light because, sorry, they're not all F light, but I don't need to look at the sample edges because I already know what the minimum spanning forest of the sample is. The point is to look at the other edges of G and ask which of them are light for that minimum spanning forest that I constructed. Okay? All right. So let's prove the sampling theorem, because the proof is very, very pretty. So the proof of the sampling theorem is a beautiful example of the principle of deferred decisions, which we've used often already. So the sampling theorem says, sample edges at random, then construct the minimum spanning tree, then see how many edges are light for the sample. We are going to do the analysis a different way. What we are going to do is we are going to construct the minimum spanning tree and take the samples while we are constructing the minimum spanning tree using the principle of deferred decisions. Okay? So what we can do is imagine running Kruskal's algorithm. On the sample. But in a weird way. What we're going to do is we're going to go through all the edges of G, smallest to largest. Okay. For each, we will check if it is connected by the lighter sampled edges we already took. Okay? So we're going to go through the edges from smallest to largest, and we're going to sample as we go. Okay? So I take the smallest edge, and I ask, is this edge connected by previous edges? No, of course not. Okay? So that tells me that whatever happens, this is going to be a light edge. Right? The smallest edge is light for everything. Okay? But what I don't know yet is whether the edge is in the sample. Right? So if I get a light edge, right? So if it is light, not connected by what came before, I will flip my coin with probability P to see if it is sampled. Okay? And either it is sampled or it is not. If it's sampled, I add it to the minimum spanning forest of the sample because it is the smallest edge, because it's not connected by the smaller edges that came before, right, in the sample. So I add it, right? If it's not, then, or sorry, if it is, right? So I've got this edge. It's not connected by the sample edges that came before, and it is in the sample. What does that mean? What can I say about that edge? It is an edge that is in the sample and is not connected by lighter sampled edges. What does our red rule say? Yeah? Yes. The edge belongs in F, which is the minimum spanning forest of the sample by the red rule. Okay. If no, so this edge does not get sampled, what does that mean about this edge? So this is an edge that is not in the sample, and the lighter edges in the sample do not connect its endpoints. Yes? Right. Is not in F, but is F light. Right? What if it is not light, right? What if it is connected by lighter sampled edges? Well, I've answered my own question, right? If it is connected by lighter sampled edges, it means it is not light, or not F light. Okay? So this is an algorithm that I'm running, and this algorithm is simultaneously constructing the minimum spanning forest of the sample, right? Right here. So this constructs the minimum spanning forest of the sample, right? And this other step is detecting, or I can say even outputting, all the F light edges, all the other F light edges, right? So the edges in the minimum spanning forest of the sample are light edges, but here are the other edges that are light. Does this make sense? Does everybody agree that this is an algorithm that is simultaneously constructing the minimum spanning forest of the sample and identifying all of the light edges that are not sampled? Everybody's happy with that? Okay. So now it's actually very easy to talk about the expected number of light edges. Okay. So it's easy because we don't really need to think too much about the mechanics of this algorithm. This algorithm is running, and a lot of times we hit this step. Edge is not F light. Okay, that's great. We don't need to think about that edge. It's not part of our count, right? We only need to worry about the case where we encounter light edges, right? Each time we encounter an F light edge, we flip a coin, right? And with probability P, we add it to our minimum spanning forest. With probability 1 minus P, we don't. Okay? Now, I'm going to take the perspective of the coin and just ask, how often is the coin flipped? Because that's the number of F light edges, right? Each time we hit a light edge, we flip a coin. So how often is that coin going to get flipped? Can it go on forever? When is it going to stop? Let me ask it that way. When are there no more flips to be done? Yes? Right. So after n minus 1 heads, we stop. How come? Exactly. The minimum spanning forest has at most n minus 1 edges. Right? So, we're flipping coins. Each one is heads with probability p. And as soon as we see n minus 1 heads, we stop. So, what can we say about how many coins we're going to flip? Yes? Exactly. The number of flips to see n heads is an inverse binomial distribution, right? A sum of n geometric random variables. Its expectation is n over p. So we're done. Right? The expected number of edges that the expected number of light edges until we see n heads is at most n over p. I think this is a lovely, lovely proof. Right? And it's just the principle of deferred decisions. You just wait to look at your randomness until the right moment. All right, so now I have filled in the verification step, right? And I will remind us that we were in this nice situation of having t of mn being, we're setting p equal a half, so t of m over 2 n plus order m plus t of 2n comma n, and that gave us this order m plus n log squared n time bound. Can we improve on this? Well, the bottleneck is here, right? Our sampling trick does this really nice job of reducing the number of edges in the graph by a constant factor, which is what you want for a linear time algorithm, right? But it doesn't do anything for the vertices, right? Because after we do the sample, we run a new minimum spanning tree algorithm on the same graph with all n vertices. The sample hasn't shrunk them at all. Wouldn't it be nice if there were some procedure that would quickly reduce the number of vertices in the graph instead of the number of edges so that we could do something about this term? How might we reduce the number of vertices? Maybe we can use some prior technique or algorithm so that we don't have to come up with something new. Maybe something incredibly old, like a century. What is an algorithm that will dramatically shrink the graph, the number of vertices, without damaging the minimum, or while making progress towards the minimum spanning tree? Such short memories. Yes? Boruvka, right? Boruvka's algorithm is a linear time procedure for decreasing the number of vertices by a constant factor. Okay. So here we'll use Boruvka. Okay. And now, because I can, I'm going to be very fussy about constants so that things work out right. Okay. To make this work, sorry, this is not the right place. Here we'll use Boruvka. But in order to make the constants work out, we're actually going to do 3 Boruvkas. Okay, 3 iterations. So this is going to transform n to n over 8 because we decrease by a factor of 2 each time we run Boruvka's algorithm. Yes? So now I can say T of Mn equals, well, let's get the boring stuff out of the way. There's linear work of running the verifier and running 3 iterations of Boruvka's algorithm. So now let's just think about the hard parts, or the recursions. So we recurse on a graph with half the edges, right? We also do a Boruvka recursion. But the important thing here is that we run Boruvka first. This is just to make the recurrence pretty. So I don't sample and then do Boruvka's algorithm. I start by running Boruvka's algorithm 3 times to get the number of vertices down to n over 8. Now, if there are only n over 8 vertices, how many edges are going to be f-light? Yes? What was that? Exactly. So there's an n over 8 here because I ran Boruvka 3 times, and there's also an n over 8 here because I ran Boruvka 3 times. Yes? And I claim that this is at most some constant times m plus n. And I'm going to prove this by induction. Or sorry, let me call this c times m plus n, right? It is order m plus n. So I claim that overall the, no, wait, sorry, I'm getting ahead of myself. That's what happens when I get too excited. Yeah, let's call this C1 times m plus n. And now I'm going to claim that this whole recurrence is at most c times m plus n. And I'm going to prove this by induction. Okay, just by plugging in, right? So here I have C1 times m plus n. Here, I can say whatever my target c is, c times m over 2 plus n over 8. And similarly here, I can plug in whatever my target c is, c times n over 4 plus n over 8. And now you can see why I decided to run 3 iterations of Boruvka's algorithm. Is that here I've got 3 terms in n, but together they only add up to n over 2. Okay? I can gather up my m terms, right? And say that I have C1 plus C. Whoops, what did I? No, right, sorry. C over 2 here times m, right? And I can similarly gather up my n terms, and that's going to be C over 8 plus C1 plus C over 4 plus C over 8 times n, which all together is equal to C over 2 plus C1 times m plus n. So I can just set C equal to C1, and I'm done. So the overall running time of this algorithm is basically just twice the running time of the verification step. And 3 Boruvka steps. Any questions? There are some ones you should be sort of reflexively asking, right? I've just done an analysis based on the expected number of edges, right? So what should you be asking? Yeah?
High probability.
Okay, so does this hold with high probability? But actually, let me back up. Is this analysis even correct? Right? I just plugged in an expected number of edges into a recurrence. That isn't always valid. Right? These running times are actually random variables. Right? And I'm treating them as if I'm acting as if I can take the expectations and use those as the expectations of these running times. Is that valid? Yeah? Why is it just linearity of expectation? Yeah? Because I'm proving a linear runtime, right? It's circular, right? I can do this trick with just treating the expectations as the actual values because it's a linear recurrence, right? If the recurrence had any nonlinear terms in it, it would be an invalid analysis. But all of these terms are linear, so linearity of expectation works. Okay? You can think of T as the expected runtime recurrence. Okay? So that works out for the expectation. Now you can ask, does this recurrence hold with high probability? And the answer is yes. You can prove that this runtime holds with high probability. Actually, the running time itself can be shown to be stochastically dominated by a negative binomial distribution, like the one that we used in the proof. Okay, so in fact, there's a Chernoff, there's a very tight bound on the running time, just based on the number of coin flips that you're going to be doing, and that's actually how you do it. You map out the whole recursion tree, and you ask how many coin flips are going to be happening over the entire recursion tree, and you get the bound. Okay. A couple of final final points to make. That beautiful proof and this nice recurrence don't use a lot about the specifics of the minimum spanning tree problem. In fact, everything they use comes from the fact that the minimum spanning tree, that spanning trees are matroids. I don't know how many of you have encountered matroids. They're kind of a weird niche in mathematics, but they turn up a lot in computer science. So MST is a particular simple example of matroid. Matroids show up every time, generally when you have greedy algorithms. Essentially, the nature of matroids is that you can, like when you take something away, it doesn't make other parts of the optimum solution non-optimal. Okay, so when we took edges away in our sample, the original minimum spanning tree edges were still optimal edges. Okay, and that's really the only feature that we relied on, and so this whole sampling technique can be applied to general matroids, and any matroid optimization problem can be solved using this sampling technique. Another thing I'll mention is that we still don't know whether there is, things are always changing, and I may have missed the announcement, but as far as I know, it is still open whether there is a deterministic algorithm for constructing minimum spanning tree in a weird way. So Ramachandran and Petty, quite a few years ago, gave an optimal deterministic MST algorithm. Okay. Unfortunately, we don't know what its runtime is. And this puts us in a very unfortunate state because we don't know what the optimum runtime is, but if anybody announces that they have developed a linear time algorithm, then Ramachandran and Petty can say, well, we already had one of those. So there's not that much motivation to actually find this deterministic algorithm. The technique is a variation on what Dixon, Rauch, and Tarjan do. Basically, Ramachandran and Petty use brute force enumeration to run the optimal construction algorithm on all possible tiny trees, and use that as the base case for a recursive minimum spanning tree algorithm whose running time is optimal because it's linear everywhere else and the only nonlinear part is in the base case. So, and actually, it's an implementable algorithm because they work with such tiny trees that they can enumerate all possible algorithms. So they enumerate all possible algorithms to find the fastest algorithm for every tiny tree, right? Because there's only a triply exponential number of algorithms. And so that's how they get the optimal runtime algorithm, but we don't know what it is because they haven't actually defined the algorithm, they just find it through exhaustive search. And that's the end of the story for minimum spanning tree. On what day of the week is it? Oh yes, on Wednesday we will look at min cuts and max flows.